Okay, we're in 14.3, talking about dilations. A dilation is a size transformation about a center point. So it's kind of like when they say they're going to dilate your pupil. If you go to the eye doctor, to dilate means to change the size of, right? When you dilate your pupil, they open it up. They put some kind of chemical in your eye that opens up your pupil, right? And then when you go out in the sun, your pupil shrinks down, and when you go in the dark room, it opens up, right? That's the dilating of the pupil. That's the changing of the size. So a dilation is a size transformation. This chapter 14 that we're in right now has been all about transformations. Transformation, how we change things, size, shape, things like that. 14.1 was translations. Translations, that's a kind of transformation. That's a movement, when you move something. And it was also about rotations. So in 14.1, we did translations and rotations. 14.2, sorry, getting a little scribbly here. 14.2, we did reflections. We reflected triangles and points and things. And now, in 14.3, dilations, changing the size of things, expanding them and shrinking them. This is our last part of chapter 14. So 3 sections of different kinds of transformations. Moving things, called translations. Rotating things, those were both in 14.1. Reflecting things, that was in 14.2. And now changing the size of things, dilations, size transformations. Okay, well, what is it? What's a dilation? Notice triangle ABC and triangle ADE. So if you'd start with ADE, that little triangle, and then if you expand it to be this bigger triangle, ABC, see how ABC is just an expansion of the little triangle ADE? That's called a size transformation or a dilation about center A, right here. This is the center. It's from that dot that we expanded the triangle, the little triangle, to be the big triangle. Now, how do we know? They say show that it's true. Well, if you notice, so this is 2, and this is 3, and then all the way from here to here is 4, right, from 1 to 5. And from 1 up to 7, this is 6, isn't it? So in other words, see how the bigger triangle is twice as big as the little triangle, right? 4 is twice as big as 2, and 6 is twice as big as 3. That's what they're saying. They're saying, AB, the bottom, which is 4 divided by AD, which is 2, is equal to AC, which is 6. That's that left side, over the small left side, 3. That fraction, 4 over 2, is equal to 6 over 3 is 2. All those fractions, both those fractions, are equal to 2, meaning that the big triangle is twice, the sides are all twice as big as the little triangle. We've changed the size, made it twice as big. That's a size transformation. So, let's try the homework. So here we go. In the following figure, the smaller triangle is the image of the larger triangle. So we're shrinking down. We start with this big triangle here, and we shrink it down to be this small triangle right there. Find the scale factor and the lengths of x and y as pictured. Okay. So remember we talked earlier in the course about expanding or shrinking shapes. So we are shrinking the size of this triangle. Whenever you expand a shape, so when we expand or shrink, meaning change the size, size transformation, a dilation. Whenever we change the size, the new image is similar. It's similar to the original. Remember that? That's what it means to be so it's not identical. It's not exactly the same. It's bigger or smaller, but it's similar, which means what? The sides have equal, let's say equal. The sides have equal ratios. That's what it means to be similar. So if the big purple triangle is similar to the little triangle, if those are similar, that means the ratio of their sides is going to be equal. So how much is it? The left side 10 has shrunk down to 6. The left side 10 has shrunk down to 6. Okay, so they want the scale factor. What's the scale factor? The scale factor is always the image over the original. You're wanting to know the image is what portion of the original. So the image is this one. This one's the image. And this one over here is the original, right? We started with the big triangle. It says the smaller triangle is the image. So the image is the 6 and the original is the 10. Now, why am I using these two? Well, because I know the right side is 15, but I don't know the right side of the little triangle. And I know the bottom of the big triangle is 13, but I don't know the bottom of the little triangle. So the only case in which I have two numbers is the left side and the left side. I have both of those numbers. So we always reduce fractions, right? So let's reduce this fraction. Divide top and bottom by 2. And so that's the scale factor, 3/5. That means the new triangle, the image, is 3/5. It's 3/5 as big. The image triangle is 3/5 as big as the original triangle. We've shrunk it down to be 3/5 the size it was. Okay, now let's use that information to help us find x. How are we going to do that? Well, we just do the same kind of thing. We say image over original, 6 over 10, or you could do 3 over 5, doesn't matter. So we're putting the image on the top and the original on the bottom. That's going to equal the x of the image over what side? The 15, right? Because the x is the right side and the 15 is the right side. Those sides have to be in an equal ratio. That's what we're saying here. Sides have equal ratios. We learned that earlier in the course when we studied similarity. If two shapes are similar, if these two triangles are similar, and they are because the small one is just a shrunk down version of the big one, it's just a size transformation, 3/5 as big as the original one, then the ratios of the sides are going to have equal ratios. These two ratios are equal, so we can use that to solve for x. How do we solve for x? Cross multiply, diagonal, diagonal, and that'll give us 6 times 15 is equal to 10 times x. Just diagonal, diagonal, and that's what? 90 is 10x. Last step to solve for x, divide by 10. Boom. So what does x have to equal? X has to be 9, doesn't it? X is 9. Now it's the same thing to solve for y. So let's do that. I'm trying to find where I've got room to do that. Let me just do it right up here. So right up here I'll solve for y. So again we start with, we're going to go 6 over 10. That's the image over the original, 6 over 10, is equal to, and now that's, now I'm going to do the y, that goes on the top because that's the image of the bottom, over 13, because that's the bottom of the big one. So let's solve for y, diagonal, diagonal, cross multiply. 6 times 13 is 10 times y. What's that? 16, 18, 78 is 10y. Last step to get y alone there, divide by 10. And so what do we get? Y equals, and they just say decimals, so it's just 7 point. Just divide on your calculator, get a decimal. They said decimals on that one. So there we go, 7.8. We got it. So when one shape is a size transformation of the other shape, then they're similar, which means their sides have equal ratios. Okay, number 2. Okay, on this one, it says A prime, let me change the color here. So A prime, B prime, this line right here, oh no, I'm sorry, this line, A prime, B prime, right? A prime, B prime. So this line right over here, this 2 centimeter line, is the image. So this one's the image. Let me write it. Oops, I don't think I had room to write that very well. There's the image. That's the image of a candle. So this is the candle. This is the original candle produced by a box camera. This is how a box camera works. So it's a little camera. Here's the little lens right there. And it lets the light through, and it produces the image on the back of the box camera. That's generally how cameras work, how they take pictures. It takes an image, which is a size transformation, which is what we're studying in this section. The height of the candle, BA, is, so how can we find the height of the camera? Of the candle. How do we find the height of the candle? Well, here's what we do. We're going to need to say image over the actual candle, the original. So we're trying to find the 2 is the image of the candle. That's the image of the candle that's displayed on the back of the box. And here's the actual candle height. Let's just call it AB. That's got to be equal to what? Well, do you see this 45 right here? This 45, which goes these two triangles have to be similar triangles because this is a size transformation. This is a size transformation. These two triangles have to be similar. Whenever you do a size transformation, the new triangle you make is similar to the other one. It's just a bigger version or a smaller version. In this case, a smaller version. So that 45, which goes through the middle of the triangle, what's the distance going through the middle of this triangle, from where the image comes in all the way to the back wall? Well, it's right there. It's that 9. That's got to be 9 right there. So, which way do I put it? Where does the 9 and the 45 go? Remember, the image is on the top. So the 9 goes on the top, and the 45 goes on the bottom. See how the AB and the 45 are parts of the original candle and the little triangle made with the original candle, and the 2 and the 9 are the image numbers. They're part of the numbers that come from the little triangle that's part of the image of the candle on the back wall of the little camera box. So we solve that those two fractions have to be equal because a size transformation always produces similar shapes. So go diagonal, diagonal. 2 times 45. Let me write that a little better. 2 times 45 is 9 times the AB. That's 90 equals 9 times the AB, the candle length, divide by 9. Boom. AB is 10. So AB or BA, whatever they want to call it, the height of the candle must actually be 10. This must be 10, and this is only 2, meaning that the candle is 5 times as big as his image. See that? This is 5 times. In other words, the image of the candle in the little box camera is 1/5 as big. And you can see the 9 is 1/5 of 45. The 9 is the distance, from all the way to the image. And 45 is the distance from the original to the hole in the camera where the lens is. And that's 5 times, right? 5 times 9 is 45. So the image is 1/5 as big. It's a size transformation, 1/5 as big. Let's try part C. If a dilation, just another word for size transformation, if a dilation with center O and scale factor R takes a quadrilateral ABCD to A prime, B prime, C prime, D prime, what dilation will take, that goes off the screen a little bit, what dilation will take it back? We'll take it, I should say back to, let me write that in here, back to that. Well, the answer is, so if A, B, C, D goes and becomes the image, A prime, B prime, C prime, D prime, that's the image, and that's scale factor R that does that, and center O, what's gonna make it go back, right? Back to the original. What will take this image backwards? We just got to do the reverse, don't you? Now what's the reverse of scale factor R? It's 1 over R. Does that make sense? For example, like this one right here. Let's go back to the last problem. So in this last problem, we said we took the candle and it went this way and it became 1/5 as big as it was. It shrunk down. 10 became 2. That's dividing by 5, isn't it? 1/5 as big. Then the other way, if we wanted to take the image back to the original candle, you'd have to multiply it by 5. See how these are the flip of each other? So to go back and forth between the image and the original, you just got to flip the scale factor. So if the original scale factor is R, now it's got to be 1 over R. So now this one's wrong because it says center OR. No. We don't want that. We want center O, the same center that we said. We don't change the center at all. The center has to be the same. So it's option B, the same center, but scale factor 1 over R. It's just the reverse. Let's see number 4. In the figure to the right, the smaller pentagon is the image of the larger. So this one is the image. This one out here is the original. Okay. Find the scale factor and the lengths of x and y. Okay. So the scale factor, remember what a scale factor is. Scale factor is the image size over the original size. Okay, so what's the original? Well, we could take a lot of different ones. We could take y as the original. That goes with 6. But we need 2 numbers. 12 with x. No. 13 with 7. There we go. 13 with 7. Oh, but I'm doing that backwards, aren't I? It's supposed to be the image on the top. The image is the 7. And the original is the 13. Yeah, I almost got that backwards. So the image is the 7. The original is the 13. Meaning the small pentagon is 7/13 as big as the original. So the scale factor is 7 over 13. Okay, now let's use that to solve for x. How are we going to do that? Well, x over 12 equals 7 over 13, huh? X over 12 is 7 over 13. The ratios have to be equal. Whenever you do whenever you have a size transformation, you create a similar object, which means the ratios of the sides are equal. Diagonal, diagonal. 13x is 7 times 12. 13x is what? 70 and 14, 84. Last step to finish solving for x. Divide by 13 on this one. And these cancel. They just want us to leave it this way. They say fraction. So instead of dividing on our calculator to get a decimal, we'll just leave it 84 over 13 for x. Now let's go get our hands on y. So how are we going to solve for y? Well, we can go 6 over y. Let's start with the image. 6 over y is 7 over 13. And then we just solve that for y. Diagonal, diagonal. 6 times 13 is 7 times y. So that's 78. And that's 7y. Last step to finish getting y alone. Divide by 7. Boom. There's y. And again, we just leave it as a fraction. 78 over 7. Okay, so there's number 4. On we go to number 5. So on this one, the following describes a dilation, size transformation, with center O. Here's the center O. An image of the segment of length 12 in bold. So here's the original. And here is the image. Right, the image is in bold. It says the image of the segment of length 12 in bold. So there's the image, the bold. It's bolded image. So it's some kind of, it's a segment. It's just a piece of a line segment. And we're blowing it up. We're expanding it, size transforming it, making it bigger. Find the scale factor and x and y. So you know how to do scale factor. Scale factor is always image over the original. So what's the image? Well, that's x over the original is 12. Well, that won't give us the two numbers we need. Right now we need two numbers. So could we take 18 over 9? We can't take y over 15. So why don't we take 18 over 9 like that? And then that just reduces to be 2, right? 9 goes into 18 2 times. So there we go. Actually, no, that's wrong. I'm kind of testing you here through this online thing. I've done something wrong. That's not actually correct. 18 over 9, I mean 18 over 9 is 2, that part's true, but 18 over 9 is my mistake. It's not 18 over 9. Why not? Isn't, right, because 18 over 9, right? Because, we did this before. We have in fact, I think we'll see it if we draw it really clearly. Let me do this for us. This will help. Let's draw the little triangle. Here's the little triangle. This is 9, 15, 12. And then right down below it, I'm going to draw the big triangle. I think everything will become really clear if we do that. There's the big triangle. This is x. Oh, what is this side here? This is 15 plus y from there to there, right? 15 plus y. And what's the bottom? 9 plus 18, meaning 27 from there to there, isn't it? Do you see we should have used 27, right? Let's try. Oh, actually, and I should have started with the, with the image. So the image triangle's the big one. And then the little triangle is the original. So we're taking the original little triangle and blowing it up to be the big image triangle. And in doing that, we got to be careful in our ratio. So image on the top, so that would be 27 for the bottom and 9 for the other bottom. It's 27 to 9. 18 was not a whole side. Whenever you're doing ratios of sides, the reason 18 was wrong is because 18 is not a whole side of any triangle. It's only part of a side. And whenever you're doing ratios of sides of a triangle, you got to make sure you have the whole side. And 18 is not the whole side of any triangle. It's just part of the big triangle. So that's the trick. It's a really common mistake students make. So that's why I tried to trick you, and I'm emphasizing doing all I can through online to reach out to you and help you not make that mistake on the exam where the points count for big. So, and just in general, so you know it when you're a teacher later, and you can help younger folks to understand the concept. 18 is not one of the sides of the triangle. The 27 is. Here, let me back up. I'm not sure. I accidentally hit the pause button, and I'm not sure how much of that you heard or didn't hear. Let's go back. I want to show you why this is the case. So back here, a really common mistake that students make is they do the following. They think, okay, I'm going to take the, I've got the image triangle, and over here is the original. So we're taking this length 12 and casting it over here to the bigger piece of x. And so they go, okay, so then how am I going to figure out the scale factor here? How are we going to find the scale factor? Well, what we could do is we could take the image on the top, got to put the image, so that would be x over 12. Well, that's not going to work because I need two numbers to figure out the scale factor, so that won't work. I might take y over 15, but again, I need two numbers. That's not going to work. So maybe I could take 18 over 9. So that's it, and 18 divided by 9 is 2, and so there's our answer. But that's wrong. That's wrong. I see that mistake a lot. So let me help with that. Why is that wrong? Because 18 is not a whole side of any triangle. That's why it's wrong. 18 is only part of the big triangle. It's not a whole side. So you can't use 18 like that. You have to use the whole 9 and 18 on the bottom, which is 27. Let me show it more clearly by just drawing the little triangle and the big. So here's the little triangle, which has got 9 here, 15 there, and 12 here. And now let's draw the big triangle, which has got, I didn't draw it too well, but right angle there. So this is x here. It's kind of bugging me that I did a bad job drawing that. There we go. Okay, x here. And then what's the bottom? It's 9 plus 18, meaning 27 all the way across the bottom, isn't it? And up here, this is 15 plus y all the way on that top there. Okay, so that's what we have to do. So getting back here, we can't use the 18, and the answer is not going to be 2. What do we use? Well, the bottom is 27, the bottom of the big triangle. And this, by the way, is the image triangle. And this little one here is the original. Right? So the image, the bottom of the image is 27, and the bottom of the original is 9. So that's going to be 3. So that ratio is 3. So watch out when you do these ratios. It's a really common mistake, an easy mistake to make. Make sure you're using a whole side of the triangle. Don't use the 18. That's not a whole side of any triangle. That's part of the big triangle, but it's not the whole side of any triangle. So the scale factor is 3, image to original, bottom of the image to bottom of the original, 27 over 9, 3. So that means the image triangle is 3 times as big. This well, I should go to make it more clear, from here to here is a times 3, right? The image is 3 times as big, right? 9 times 3 is 27. The new one's 3 times as big. Okay, so we can use that to help us find the other parts. Like, let's find x. How are we going to find x? Well, we start with the image, so x over 12 is equal to what? 27 over 9. Just keep using that 27 over 9. So we can solve that equation now for x, diagonal, diagonal. 9 times x is 12 times 27. Use my, was that 270 and 54? I don't know. 27 times, 27 times 12 is 324. And last step, divide by the 9. And so x equals 36. So x is 36. Now let's do the same thing to solve for y. I'll do it right over here. So we'll take the image, 15 plus y over 15, right? The top over the top. I probably need a little more room here. I'll move this out of the way and come up here. 15 plus y, the top up here, over 15. It's the image over the original, equals 27 over 9. 27 over 9. Okay. So, there we go. We can solve that equation for y, diagonal, diagonal. It's going to be 9 times 15 plus y. That's 15 times 27. And so, distribute that 9. 9 times 15, 135 plus 9y. And 15 times 27, I don't know what that is. 405. Got to solve here. Let's subtract 135. And we get 9y equals, what is that, 270 or something? Yeah, 270. Last step to finish solving for y, divide by 9. And y equals 30. So y is 30. So we got it. All right, good. So now on to the last one, number 6. Let me see. I'll move these out of the way so we can read it. So what sequence of transformations will transform a circle with center O, radius 3/4, onto a circle with center O2, radius 9? Well, what are they talking about? They're saying they've got some kind of circle, and so maybe if you have a coordinate, you have some kind of circle. The center is O, and it's been moved to a new center. So I don't know, they moved it to some kind of new center O2. So they changed, they grabbed the center and they moved it. And then the old radius was 3/4. From the middle to the edge here was 3/4. The new radius is much bigger. That wasn't a very good drawing there. That's the best I can do. The new radius is 9. New radius is 9. Okay, so what's going to make that happen? How does that work? Well, you've got to take O to O2. You've got to move the center, and then you've got to do some kind of size transformation. 3/4 has got to become 9. This is the image, right? And the 3/4, this one over here, is the original. So remember what a scale factor always equals. Scale factor is always equal to the image over the original. So the image has a radius of 9 here, right? 9. And the original is 3/4, is his radius. So the image 9 over the 3/4. Now, what do you do with that fraction? How do you deal with a fraction divided by a fraction? That's kind of weird. I don't know if you've seen that or know what to do about that. But basically, you think about with me rather than just telling you. Let me give you logic for it. So you know if I take a number like 10 and I divide by 2, that's 5, right? And what if I take 10 times half? What's half of 10? Well, same thing, 5. Right. So dividing by 2 is the same as multiplying by a half, isn't it? In other words, dividing is just multiplying by the upside down. This is the upside down of 2, the 1 over 2. Right? So dividing and multiplying are just the same thing. They're just upside down. So instead of dividing by 3/4, it would be easier if we flip it up and we make this 9 multiplied by what? 4/3. See how I flipped it upside down? Because multiplying is upside down dividing. Just like dividing by 2 is multiplying by the upside down. So if you divide by a number or a fraction or anything, it's the same as multiplying by the upside down. So multiply by the upside down. Now how do you do that? Let me bring that over here. How do you take 9 times 4/3? Now that I've changed it from a dividing problem to a multiplying problem, how exactly do you work that out? Well, a whole number interacting with a fraction, we put it over 1, make it look like a fraction. And then remember what you can do when you're multiplying fractions? 3 goes into 9 3 times. So what are we left with? 3 times 4, 12. There's the answer. Or, having said all that, or let me tell you, you could take 9 divided by 3/4. 3/4, you know what 3/4 of a dollar is, right? What's 3/4 of a dollar? 0.75. So if you just take your calculator and go 9 divided by 0.75, you'll also get 12. In other words, 75 cents goes into $9 12 times. But I like the fraction way, because dividing by a fraction is the same as multiplying by the upside down, because multiplying and dividing are just upside down operations. And then you put the 9 over 1, cross cancel, 3 times 4 is 12. There we go. There's our answer.